Hello everyone, welcome to statics course. So we are to about the chapter 9, which is the last chapter of the whole semester. Wow! So chapter 9 is talking about the center of gravity. Okay, and there are center of mass, or center of the volumes, or center of the line. How we can find the center if we have a like a very different shape of the 3D rigid bodies. Okay, let's look at today's goal is understand. No, you don't need to memorize this. Okay, I'm going to explain some concept, but you don't need to memorize this. This is just I want you to understand how we get that equations to find the center of gravity, center of mass, center of volume, center of area, and lastly center of line. Okay, let's check some application first. Okay, so when I explained the distributed load, I think it was chapter 4 or something. You may realize that we can calculate the water's weight. Okay, the water contacting the surface of the water tank, and each particle of water has a weight, and then we can say that has a weight, and we can say that the total weight of water, we can just do the integral of the distributed the small particle of water's weight. Okay, so the same concept when we design this water tank, we always want to check the weight of the water and where is the center of the gravity, because that's the reason why we can put the support at the right positions to securely hold the weight. Okay, so this one will not collapse. So we want to know where is the resultant force, where's the line of the resultant force. Okay, another one is when we design the sports utility vehicle SUV. The one concern when we design the SUV is a tip over when you make a sharp turn. Okay, since SUV has a relatively higher center of gravity above the ground, we may need to adjust the center of gravity to avoid the unexpected situations. So center of mass, center of gravity, center of mass in this case is relatively higher than the sedan or a sports car. So question is, should it be the center of gravity of the SUV, should it be higher or lower to prevent the tip over event? It should be lower, right? Why? Because the lower center of gravity has the lower moment from the ground, about the ground. So if you see the perpendicular distance from the ground, it should be lower. That creates lower moment. So that's why we need to lower the center of gravity to prevent the tip over event. The last concept is, I think if you have a chance to see a football stadium, you may see this kind of goalpost. The goalpost has different structures. See here we have some shape here and another shape here. This is actually two components. In this case, how we can find the center of gravity and center of mass? That's the reason why we have to use the integration. Do you remember these things? Y equal integral x dx. So we have to use integrations. All right. So now let's explain how to find the center of gravity. Let's see, this is the sand, and the sand has so many particles, small sand. There are thousands of the sand to create this object. Let's call this is a chunk of sand, and this is the rigid body. Let's assume. So each particle, that means each sand has a weight. Obviously, this sand has a weight. This sand has a weight. There are so many weight. So you may recall, oh, it looks like a distributed load, right? Yes, that's the exactly same concept. We have a small, tiny particle, and that particle has a weight. Let's say that particle has a weight which called differential weight. When you add up all the differential weight, that should be equal to what? That should be equal to the total weight of this entire sand. So this is easy concept, right? So where is the center of the gravity of this entire sand? Okay. The first thing, we just learned this concept, the total weight of this sand, rigid body, is equal to integral all the differential weight. Okay, so remember that there are so many particles has a weight. Each particle's weight is differential weight. We can add up all the differential weight, that is the weight. So center of the gravity is the point of the line of actions that the total weight, the resultant weight, is activated. So here, center of gravity, we don't know where it is yet, but we can assume that, oh, this is the where the resultant force acting on the line. Okay. So why we need to find the center of gravity? Since we have so many particles, we can simplify the problems. Okay, just a small particle. Even though we have a lot of sand here, we can assume that, okay, there is only one particle, which is a rigid body, and the total weight would be the uppercase W. Okay, so we can simplify the problem. The second region is, this is not the reason, this is just information. For a rigid body in near Earth gravity, center of gravity is equal to center of mass. And also, if the object has a uniform density, then the center of gravity, center of mass, is equal to centroid of the volume. If the object has the uniform density. Where is the centroid? Centroid, here you can see the square, boxes, and the circle, and rectangular, and the line. All the centroid is in the center, in the middle. So you can find some cross the lines and find the intersectional points that can, separate symmetrically. Okay, so for example, in this rectangular boxes, you can draw the two lines that can separate this part symmetrically. So in this case, the center is the centroid. Actually, the line is the easy. The half is the you can fold this line symmetrically. So yeah, so the center is a centroid. So let's go back to the center of gravity. If you remember the sand that I explained just a minute ago, each particle of the sand has a differential weight. We call that is differential weight, and this particle has a location. Okay, in 3D we can say the location of this small particle is x tilde, y tilde, and z tilde. How about the center of the gravity? Center of the gravity is represent all the particles weight with the total weight. The total weight should act on the line of the center of the gravity part. The point center of the gravity is here. So center of the gravity, we can say x bar, y bar, and z bar. So please remember there is a difference between location of a particle and the center of the gravity. Okay, so location of a particle, x tilde, y tilde, z tilde. Center of gravity, x bar, y bar, z bar. They are different. It could be same, but it's different. Right. So you have to understand this. This is very important concept. So here we have x, y, z coordinate systems. You can see x-axis, y-axis, and the z-axis. We can calculate the moment about the x-axis of this small particle. Like I said, the location of this small particle is x tilde, y tilde, and z tilde, and there is a weight, which is a differential weight. Then what is the moment of this differential weight about the x-axis? So we can calculate the perpendicular distance from the x-axis surfaces, xz surfaces, which is y tilde. You can see this is the coordinate x tilde, y tilde, z tilde. So the perpendicular distance from this surface xz plane to the particle is y tilde. So y tilde times dw is actually moment, which is clockwise rotations. So it's I think this is the negative direction to the x-axis, but this is not the direction is not important in here. So you can say that, oh, okay, differential moment about x-axis is y tilde times dw. Okay. So we want to know that if we calculate all the differential moment about the x-axis, that means we can add all the differential moment about the x-axis is equal to resultant moment about the x-axis. Okay, then the resultant moment means it's a resultant moment about x-axis. That means we can find the center of the gravity, where is the line of actions. So the sum of the moments due to individual particle weight about any point is the same as the moment due to the resultant weight located at G. So integral differential moment is equal to resultant moment. And this resultant moment will work at the line of the center of the gravity. So center of the gravity, let's say this is G. Now you can see that we can say this is x bar, not x tilde, x bar, y bar, and z bar. There is a center of the gravity. So the same concept, resultant, we know that the center of gravity, there is a weight, which is uppercase W. This is the total weight of this all sand. So total weight is integral differential weight. So now what? Resultant moment about the x-axis is equal to integral differential moment about the x-axis. Then we can say that differential moment is equal to integral y bar d no let me see differential moment about x-axis is equal to differential weight times y tilde. Yes, okay, we can say like this. But basically what we already know is that resultant moment will act on the center of the gravity, and we know the perpendicular distance from the xz surface to the center of the gravity is y bar. Here you can see that y bar times integral dw. What is the integral dw? That is the total weight. So one more time, guys, when we calculate the resultant moment about the x-axis, here we have an x-axis, and this particle is has a weight that is the w, and this w is the all summation of all the weights of the sand. So we can calculate the y bar is resultant moment about the x-axis divided by the total weight. So now we have one equation to find the center of the gravity. Again, the resultant moment about the x-axis is equal to y bar. Y bar is the y location of the center of the gravity times integral dw, which is the total weight of the sand. So we can express this way: y bar is equal to resultant moment about x-axis divided by the integral differential weight. Resultant moment about x-axis, this one, we can say that, oh, that means resultant moment is, we can add up all the particles moment about the x-axis that should be equal to resultant moment. So here we have another integral y tilde. Y tilde is what? Tilde is a location of a particle. So integral y tilde times differential weight, each particle's weight. So y bar is here. How about the x bar? Same thing. X bar is integral x tilde times dw over integral dw. How about the z bar? Z bar is equal to integral z tilde times dw and integral dw. So you can assume that we can calculate the moment about the y-axis and x-axis and z-axis. You will end up to find these equations. Okay, so this is a little bit complicated concept, but if you know that, okay, this is the resultant moment of the weight and this is the total weight, then we can say, oh, okay, where is the line of actions? We can just divide by the two items. Y bar is a resultant moment about x-axis and total weight. So we can, that's the how we can find the y bar and the x bar and the z bar. This concept is, I will just simply explain how we can get a center of mass. Now we find the center of gravity, which is in blue. you can see X bar, Y bar, and Z bar. Center of mass is the same concept. If you remember that weight is the mass times gravitational acceleration. In this case, gravitational acceleration is always constant. So differential weight is equal to gravitational acceleration times differential mass. Okay, so dw equals to g times dm. So in this case, we can say, okay, dw is equal to g times dm. So we can say x bar is here, y bar is here, and z bar is here, and the g will be cancelled out. So in yellow form, this is the center of mass. X bar is equal to integral x tilde times differential mass over the total mass, integral differential mass. So what you can see here is we just simply change the differential weight to differential mass. And here you can see the denominator part also we just changed from the differential weight to differential mass. Okay, that's pretty much it. How about the center of the volume? So we know the center of the mass. If you remember the density equation, density is affected by the mass and the volume, and the mass over volume is the density, which means mass is equal to density times volume. Okay, this is the simple transitions. Then the density, we can say this is the constant, like a gravitational acceleration, what we just saw before. So we can say that density is a constant. So differential mass is equal to rho times differential volume. Now we can just change the differential mass to differential volume for the numerator and the denominator part. So that's pretty much easy one. Another one, we want to know the center of area. So area is what? Volume is area times height. Okay. Let's say height is the thickness in this case. Thickness is, we can consider this is also a constant. So we can change dV to dA. Okay, so where is the center of the area? We don't have a z bar here because area is a two-dimensional cases. So only x bar and y bars are here. So x bar is equal to integral x tilde times dA over integral dA. Y bar is integral y tilde dA over integral dA. What is the integral dA? Differential area, and you add up all the differential area. That means the total area of the surface. Okay. The last concept is the center of line. Since we know the center of the area, then area is what? Area is width times length. Let's assume this width is the constant. Then we can say, okay, x bar is equal to x tilde dl over integral dl. So that means integral dl is just L. Okay, so you don't need to memorize this again, just understand the concept. This is easy concept. When you want to calculate center of the area, then you can just find a differential area. That's it. If you want to find the center of a line, then you can just simply find differential length. It's depending on how you define what is the differential area and the differential length based on the questions. But this is the simple concept. Alright, so let's solve the one example so you can guess more ideas how to find the center of the gravity, center of the mass, and center of the volume, center of area, and center of line. So question here is to find the center of area. Okay, center of area of this triangle. If you look at this triangle, the rise is h and run is b. We have a dimension here. Oh, by the way, the textbook gives you the right answer. It give you already the answer. This is the center of these triangles because we have these dimensions. Then we already know that the center of this triangle, center of area of this triangle is 2 over 3b. Where is the b? B is here, so 2 over 3b is somewhere here. And 1 over 3h. Okay. We already know the locations, the center of the area. All right. Then how we can find? We already know this one, but how we can find this one using the equations? So if you remember that x bar, which is the center of the area, is equal to integral x tilde dA, because what we are looking right now is the center of area, over dA. Y bar is integral y tilde dA over dA. Does it make sense? Let me just double check. Okay. All right. Okay, so let's use these two equations to find the center of area of this triangle. Before we start, let's define the differential area. In the textbook, they define the small box. Here you can see the box here. This box is has an area. Let's say this box is very small, and this is differential. Differential area is equal to what is the what is the right part? This part. Oh, I think let's see. Yeah, we can apply these two equations. Okay, so we can say that there is a, okay, let's put it this way. This is the x-axis and this is the y-axis. My drawing is really bad. So y-axis, and we can draw the line along the surface. Then we can draw the equation y is equal to h over bx, this line. Okay. Let me draw another color. I use a black one. Okay, we have a line that passes through the 0.0 here. This is the equation. Y is equal to h over bx. So in this case, this point is x comma h over bx, because we plug the x is into these equations. So y is h over bx. Anyway, so what is the differential area of these boxes? Differential area. Area is height times width, right? So height is h over bx, and the width is differential x. Here we have a differential x. So we know this equation. dA is equal to h over bx times dx. And the center of this small particle is x tilde and y tilde. You have to understand this one. dA, what I just showed you, is h over bx times dx. So now let's use the equation where we already know that x bar, that is the center of area of the x. The x bar is equal to x tilde times dA, integral. Okay, over integral dA. And we already know that dA is actually I missed the tilde here, but there is a tilde, okay? So integral x times h over bx times dx. And the denominator part, we already know the differential area, that is h over bx times dx. Now we can solve these problems using the integral equations, and we can find dx is 2 over 3b. X bar is 2 over 3b. You can find the equations. How about the y bar? We can say, okay, this is the differential area we're gonna use. In this case, the height is the dy, and what is the width? Width here is again differential area of this small particle is dy times b minus b over hy. This is the width of this differential area. You can check my equations here. Now we're gonna use the dA using this horizontal bar. Y bar is equal to integral y times dA over the integral dA. So we're gonna solve this dA about the dy, okay, which is different compared to the previous one about the dx. Here we have a dx here, but now we're gonna solve the problem about the dy. Then you can find that y bar is equal to 1 over 3h. So this is the answer. This is the center of the center of area of this triangle. You can find the centroid informations. Simply search the Google. For example, we have a half circles here, and where is the x bar, and where is the y bar, and what is the equation of the area. Alright, today we learned how to calculate center of gravity, mass, volume, area, and line using the moment equations. Thanks for watching this short video. Have a great day.